Hi everyone, welcome to AI Crack channel. This is Akash Gangar and today we'll be studying relations lecture 1. This is the only lecture for relations and after that we'll be starting with functions. So let's begin a lecture with cardinal number of sets, which is nothing but a fancy name for the number of elements in a particular set. Let's say we have the set A equals to 1, 2, 3, 4. Now in this case cardinal number of set A would be 4. Why? Because the number of elements in this case is 4. But as of now, we are more interested to understand the number of elements in A union B, number of elements in A union B union C. Until now, we have just seen how to present them in visual format of Venn diagrams, right? We just know how to present them in Venn diagrams, and we have done the calculation with the help of manually counting. Right? We didn't have any kind of formula over there to find out the number of elements in A union B or A union B union C, right? So let's try to derive the formulas of number of elements in A union B. For that, we'll be considering two sets as an example. A equals to 1, 2, 3, 4, 5, let's say, and B equals to 4, 5, 6, 7. Okay. Now, if you want to present this in Venn diagrams, this would look like this, right? This is our set A, this is our set B. And in case in A and B, we have 4 and 5 is common. So 4 and 5 would come over here. 1, 2, 3 would come over here. 1, 2, and 3, and 6 and 7 would come over here. So basically this region is containing all the elements which are present only in A. This region is containing all the elements which are present only in B, and this region is containing the elements which are common in both A and B, right? So what I can understand from this one is any particular set can be divided into two regions. The first region is presented by a dot which contains all the elements present in only that set. The second dot represents the other part of the set which contains element which is common between A and B, or basically both of the sets, right? So we have divided a particular set into two parts. Now we'll be utilizing that to derive our formula. So this is our set A, this is our set B. Now if I'm writing NA plus NB, to represent NA, I would be using one dot over here and one dot over here, right? Because that's how we have to calculate the total number of elements in A. Some elements are over here and some elements are over here. To represent NB, I have to again put a dot over here and a dot over here, right? But if I have to calculate NA union B, we have to oblige with the basic property of set that there should be no repetition of elements, right? We cannot write a set like 1, 1, 2, 2, and so on, right? We cannot do that. We have to write element one single time, right? So what we have to do, we have to remove this extra dot. What is this extra dot? This is the element. These are the elements which are common in both A and B, and that is being presented by NA intersection B, right? So NA union B comes out to be NA plus NB, which was presented by this dot, this dot, this dot, and this dot, subtracting this particular dot, basically, which is NA intersection B, right? So this is how our formula came for NA union B. Now, in a similar manner, we'll be doing NA union B union C, but for that, I'll have to divide my entire set into four regions. This region, this region, this region, and this region. Let's say this is our set A, set B, and set C. Now, if I'm writing NA, in that case, this, and this dot. Okay. If I'm writing plus NB, in that case, one dot over here, one dot over here, one dot over here, and one dot over here, right? If I'm also writing NC, one dot over here, one dot over here, one dot over here, and one dot over here. Now we can see a lot of overlaps over here. So we have to remove all those overlaps. Now, if I want to remove this overlap one single time, I'll have to cross this one and cross this one. That would give me n of A intersection B, right? If I want to remove this one and this entire region, that would give me minus n of B intersection C. If I have to remove this one and this one, in that case I'll be having minus n of A intersection C, right? Now, but in this case, we have got a single dot in every place except this one. So I'll add one more dot over here. So basically getting NA intersection B intersection C, right? So this is how our formula came for NA union B union C. That is NA plus NB plus NC minus NA union B minus NB union C minus NA union C plus NA intersection B intersection C, right? Now let's talk about Cartesian product or cross product, and let's first read the formal definition. The Cartesian products of sets mean the product of two non-empty sets. This is important. In an ordered way. This is the most important keyword over here. Or in other words, the collection of all ordered pairs obtained by product of two non-empty sets. An ordered pair means that two elements are taken from each set. So what do we mean by this? Let's say we have a set A, that is 1 comma 2 comma 3, and the other set is B, that is A comma B comma C. Let's say we have this set. Now what we are doing in case of cross product A cross B, we are taking one element from A and the other element from B and combining them to form a single element of A cross B. And similarly, we are doing this for all the pairs, all the possible pairs in an ordered way. We cannot do A comma 1, 1 comma B, A comma C. We cannot do that. We have to take one element from A, the other element from B. And if we are writing A cross B, so the first element should be from A and not from B. First element should be from A and not from B. So similarly, we can take all the pairs, all the possible pairs over here. So 1 comma B, 1 comma C, 2 comma A, 2 comma B, and so on. We can write all the elements over here. Now, since every element of this set is being paired with every element of B set, so the total number of elements would be NA multiplied by NB. So if we have A elements over here and B elements over here, so total number of elements would be A into B, right? Now if we write B cross A for the same set, we would be writing B comma 1, B comma 2, B comma 3, and so on. All 9 elements over there. But we can never say that B cross A would definitely be equals to A cross B. It's not possible unless A equals to B. This is the only case where B cross A would be equals to A cross B. Otherwise, in all the cases, A cross B and B cross A won't be equal because of the ordered pairing. 1 comma B is not equals to B comma 1, right? Now let us talk about relations. So formally, a relation is nothing but a subset of A cross B. So let's define set A as again 1 comma 2 comma 3 and B as what, let's say A comma B only. So we have total number of 6 elements in A cross B. Let's write all those elements. So 1 comma A, 1 comma B, 2 comma A, 2 comma B, 3 comma A, 3 comma B. So these are all the 6 elements of A cross B, right? Now if I want to write a subset of A cross B, let's say that is R1, that would be, let's say 1 comma A, 2 comma A, and 3 comma B. So this is a subset of this, right? This relation is a subset of A cross B because all these elements are also present in A cross B. Okay. Now, if we go back to our set theory lecture, we saw that if we have n number of elements in a particular set, then we have total number of 2 raised per n subsets, right? So for A cross B, we have A into B, where A is NA and B is NB. We have AB number of elements in A cross B, right? So total number of subsets or total number of relations corresponding to A cross B would be 2 raised per AB, right? Now it includes all those improper and proper subsets. But in case of relations, we call them with a different name. Okay. So the improper set was which was there in set theory is called as universal relation over here. Basically, where the subset is nothing but A cross B only. Where the relation over here is nothing but A cross B itself. That is called as universal relation. Now the in the other case where relation is nothing but an empty set, there we used to call it as a null set or a phi. In this case we just call it as an empty relation. Okay. Now if you remember, we used venn diagrams for visual representation of sets and their operations. In case of relations, we'll be using arrow diagrams for their visual representations. So these are the arrow diagrams. Now we have set A as A comma B comma C, we have set B as 1 comma 2 comma 3, and in A cross B we'll be having 9 elements, right? And out of those 9 elements we have chosen 3 to form this subset, that is a relation. right? Now, how to present this relation in arrow diagrams? First of all, we have to understand when we are writing A cross B, in case of arrow diagram, that means we are going from A towards B, right? Now, the element, first element over here is A. So we'll start our arrow, we'll originate our arrow from A towards 1, like this. Similarly, for B comma 2, we'll start our arrow from A, B and end towards 2. And for this element C comma 2, we'll start our arrow from here and it would go towards 2, right? So this is our arrow diagram for this particular relation. Now in set B, the elements which are being mapped are called the images. There is no name for 3, but the elements which are being mapped, 1, 2 over here, are called as the images. So 1 is the image of A, 2 is the image of B, and 2 is also the image of C. And the elements of set A from which the mapping is starting, these are called the pre-images. So A is the pre-image of 1, B is the pre-image of 2, C is the pre-image of 2, right? Now let us talk about domain, codomain and range. Now we have set A as A, B, C, D and set B as 1, 2, 3. When we write A cross B, we'll be having 12 elements over here. In this set, we'll be having 12 elements, right? This is NA cross B, that would be 12. This is our set A, set B. We are going from A to B, right? Now we have this relation D comma 1, B comma 2 and C comma 2. So this is our relation. Let's say this is R1, okay? Now when we are defining domain, now the elements from which mapping is starting, all these elements are being considered in domain. So D over here is B comma C comma D, right? Now when we are writing codomain, codomain is nothing but set B. So set B is 1 comma 2 comma 3. All the elements of set B, basically the other set, that would be 1 comma 2 comma 3. All the elements would be codomain. Okay. Now if we talk about range, range would be all the elements which are being mapped. So over here, the elements which are being mapped are 1 and 2. So that would be range. Let me repeat it once again. For domain, all the elements from which mapping is starting. So if we are defining from A to B, so mapping is starting from A. So that's why all the elements of A from which mapping is starting is B, C, D. So that's why they come under domain. For codomain, all the elements of the set where mapping is ending. So in this case, mapping is ending at B. So all the elements of B is the codomain. Now, in case of range, all the elements of B which are being mapped, that is range. Okay, so 1 and 2 over here are being mapped, so that's why range. Now we know that relations are nothing but subsets of A cross B or cross product. So that's why they are also represented the way sets are presented, right? So in roster form, set builder form. We won't be repeating this in this lecture. You can take a refresher from the set theory lecture. Now let's talk about types of relations. So we have 4 types: symmetric, reflexive, transitive and equivalence. And this is one of the most important topics of relations if we talk about PGDBA, right? Now let's start with symmetric. It says that if A comma B is present in a relation, let's say we have a particular relation and A comma B is an element of that relation. In that case, for it to be symmetric, B comma A should also be present. If A comma B is there in that relation as an element, for it to be symmetric, there should be B comma A as well in that relation, right? So if B comma A is not there, that won't be called as symmetric, right? Very simple. Let's say we have relation 1 comma 2, 2 comma 3, 3 comma 4 and 2 comma 1, 3 comma 2 and 4 comma 3. So in this case, for 1 comma 2 we have 2 comma 1, for 2 comma 3 we have 3 comma 2, for 3 comma 4 we have 4 comma 3. We have to check for all the elements. So we have 3 possible elements over here for which we have to check the reverse, basically symmetric part: 2 comma 1, 3 comma 2, 4 comma 3. So if we have just one missing over here, in that case it won't be called as symmetric. We have to have all the elements with this kind of format. Okay. Now if we talk about reflexive, So if we have a comma b in a particular relation, for it to be reflexive, we should always have a comma a also, right? For it to be reflexive, we should always have a comma a, given that we have a comma b present in the relation, right? That's again very simple. Let's say we have an example. We have 1 comma 2, and we have 2 comma 3, and we have 1 comma 1, and we have 2 comma 2. Now this is an example of a reflexive relation. We have 1 comma 2, that's why we have 1 comma 1. We have 2 comma 3, that's why we have 2 comma 2. We have 1 comma 1, that's why we have 1 comma 1. We have 2 comma 2, that's why we have 2 comma 2. We have to check for every single element if we have the corresponding pair or not, right? Now, if we talk about transitive, that is the trickiest one. So that says if we have a comma b and also we have b comma c, in that case, for it to be transitive, we should have a comma c in the relation as well, right? What do we mean by that? Let's say we have a relation 1 comma 2 comma 3 and 1 comma 3. So we have a comma b over here, we have b comma c over here, so and also we have a comma c. Now given that these two are present, in that case, if this is present, then it would be a transitive relation. If this is not present, let's say this is 1 comma 4, in that case it won't be a transitive relation. Now the important thing over here is we can have a relation like 1 comma 2 2 comma 3, 2 comma 4, 1 comma 3. Now in this case we have two pairs for 1 comma 2. So we have 1 comma 2 as a comma b, and it has two corresponding pairs for b comma c. One is 2 comma 3, the other one is 2 comma 4. So we should have 1 comma 4, and also we should have, sorry, 1 comma 3 and 1 comma 4. So we should have both of these elements for it to be transitive. In this case we have just 1 comma 3, we have just 1 comma 3, we have this pair, this complete pair, but we don't have this complete pair. Since we don't have this complete pair, so that's why it's not transitive. Okay. Now the last one is equivalence. If a relation is symmetric, reflexive, and transitive, then it's called an equivalence relation. So basically the game is of on only these relations. This is just a consequence. Now let's look at this example, these two examples. We have this relation 2 comma 3, 2 comma 4, 3, 4, 4, 5, 4, 4, 5, 5. So let's look at symmetric, reflexive, and transitive. Now we have 2, 3. For it to be symmetric, we should have 3, 2 over here. Do we have 3, 2 over here? No. So that's why it's not symmetric. Now for reflexive, we have 2, 3. Do we have 2 comma 2? For 2 comma 3, we should have a 2 comma 2 in that relation. If we don't have, then it's not reflexive as well. Now if we talk about transitive, let's start building pairs. So the first element is 2 comma 3. So we have 2 comma 3 and we have 3 comma 4 over here. So what we should have, 2 comma 4. Do we have a 2 comma 4? Yes, we do have. Now this pair is successful. Now let's look at 2 comma 4. Also, before looking at 2 comma 4, is there any other pairing possible for 2 comma 3? No, we have just 2 comma 3 and 3 comma 4. So there is no other pairing possible for 2 comma 3 and 3 comma 4, right? Now let's talk about 2 comma 4. What kind of pairs we can make? We can have two pairs over here. That is 4 comma 5 and 4 comma 4, right? Now in this case, do we have 2 comma 5? In this case, do we have 2 comma 4? We do have 2 comma 4, right? But do we have 2 comma 5? There is no 2 comma 5 over here. So that's why this is also not transitive. So we have to check all the pairs over here. We could have gone just through with this pair and we have marked yes for transitive, but it's actually not, because we have to check this pair as well. We have 2 comma 4, 4 comma 5, but we don't have 2 comma 5. So that's why it's also non-transitive. Now let's look at this example. Now we have 3 comma 4 and 5 comma 6. So for symmetric, reflexive, and transitive. For 3 comma 4, do we have 4 comma 3? No, that's why not symmetric. For 3 comma 4, do we have 3 comma 3? No. So that's why not reflexive. Now we have 3 comma 4 and we have 5 comma 6. What do we mean by transitive? We mean that if we have 3 comma 4 and if we have 4 comma something, let's say 4 comma 8, then we have 3 comma 8. But we don't even have a pair for 3 comma 4. We just have a 3 comma 4 over here, and we have 5 comma 6 over here. There is no further pairing. So because the given condition is not following, we have to mark it as transitive. Only in case we have 3 comma 4 and we have a pairing of, let's say, 4 comma 9, and we don't have 3 comma 9, in that case we cannot say that it's a transitive relation. And similarly it goes for 5 comma 6, we don't have any kind of pairing, so that's why it automatically becomes transitive. Now let's talk about this example. We have this relation x comma y where x is a sister of y. What type of relation is this? So this basically means we have all the elements. This is written in set builder form. So we have all the elements x and y where x is a sister of y, right? Now when we say that x is a sister of y, then definitely means that x is female and y can be male or female. In both the cases, x is sister of y, right? But when we have to talk about symmetric, we have to do the opposite. We have to write y1 and y2. This one is male, this one is female. And we are doing the opposite. This one is female. Can we say that y1 is a sister of x? We cannot say that, right? We cannot say that. So that's why it's not symmetric. If someone is getting confused in terms of y1 and y2, let's take the names over here, right? Now let's define the two elements of this set. Okay. So the first element is Neelam, which is x, comma Akash, which is y1, right? Second element would be Neelam and say Shreya. Okay. Shreya is y2. Now both elements are being satisfied by x is sister of y. Neelam is sister of Akash, Neelam is sister of Shreya, right? Now for it to be symmetric, we have to do the reverse. We have to write Akash and Neelam. We have to have this element in this set. But is it possible? Is Akash sister of Neelam? No, it's not. So that's why it's not symmetric, right? Now for it to be reflexive, that basically means given that x is sister of y, x is sister of x. Is it possible? Can one be sister of herself? Right? Not possible. So that's why not reflexive as well. Now the third case for transitive. For transitive, we have x is sister of y. That basically means x is female and y is something else, male or female. Let's see. And also y is sister of z, right? But now we have said that y is sister of z, that means y is also female. Now z can be male or female, right? Now we have to say x is sister of z. Is it true? Yes, it's true. It includes all the elements where x is sister of y is sister of z, and x is sister of z, right? That's true. Because this is female, this is female, this is female, this is male comma female. But if we combine x and z, this is also true, right? So that's why it's transitive. It's not reflexive, it's not symmetric, but it's transitive. Now again, if you get confused with these variables, you can take the example of names and you'll be able to get the answer. But these are the kind of difficult questions which you can expect in PGDB examination, right? And now I leave this question for the homework. And this entire lecture was still here only. And let's meet in the next lecture for functions. Thanks for watching.